All right, howdy folks. Welcome back to Professor Carbon. In this video, we're going to go through a number of reactions, both of dienes, but also ethers and epoxides. And I really like these because they should be kind of rapid fire. And so they're always keep me on my toes. All right, so let's dive right in. In this first problem, we're asked to put something in the box here that would be a starting material. And this means we have to think backwards from what the product is using the other starting material over here. Now, if we think about it, I always try to latch on to something in the product that looks like something in the starting material kind of as a point of reference. And here it's going to be this OCH3 ether, and then we've got a CH2 unit, and then we've got a 5-membered ring. And so with that information, then I can follow this 5-membered ring like so. And that means whatever has to go in this box has got to have this component here. And sometimes it can also be really handy to know exactly what functional groups are there, identifying the reaction that formed this product. In this case, it's going to be a Diels Alder reaction. And we get there, of course, by reacting a diene with the dienophyl. And we have our diene right here. So that's our diene. And that means we're going to put the dienophyl in the box. And then we're going to have a chloride and a cyanide or nitrile group coming off of the same carbon. And so there you go. And it turns out this particular example is from this famous 1969 total synthesis by E.J. Corey's lab. And so it's kind of a fun historical context for this relatively straightforward Diels Alder reaction. Moving right along, let's see here. Oh man, this is one where we have two boxes now. That makes it hard because now we're going to have more possibilities and things to consider. So let's check out our starting material again. And we have this nice phenyl ring. And so right here, we've got a phenyl ring. We've got a CH2, got a CH2, got an oxygen. So that's good. So we're going to somehow have to put all of this stuff in the box. And of course, this functional group in the middle here is an ether. And when I hear ether and making an ether, I jump right away to the Williamson ether synthesis. And that's good because we've got an alcohol. That's one of the two things that go into the Williamson ether synthesis, one of the three things really. And so then we need an electrophile and a base. And so we're going to need sodium hydride as a kind of our favorite base for the Williamson ether synthesis because it'll fully deprotonate that benzyl alcohol to make the alkoxide, NaH. So that's kind of the point of reference. And now we've got a strong nucleophile for an SN2 reaction. And the thing that we need to throw in here for our SN2 reaction is going to be allyl bromide or iodide or chloride. It could be whatever allyl X we want. It could be tosylate. You can pick and choose from there. And so this would totally work. I think that that's fair. There is another possibility here as well that I guess I should probably accept points for if I just delete all of this. The Williamson ether synthesis would be my kind of preferred method for reasons I'll mention here in a moment. But we could also imagine having allyl alcohol and using some kind of acid catalyst like H2SO4. That would make this ether, but it would make it in a random way that's complicated by a number of other carbocationic intermediates. So the way that you generate this ether from these starting materials and sulfuric acid is you protonate the OH, you make a carbocation, and then that carbocation would be attacked by the alcohol. But since we know that alkenes can attack carbocations, and we'll learn that arenes or benzene rings can attack carbocations, and you'd also have a random distribution then of which alcohol made the carbocation and which alcohol attacked the carbocation, that reaction would probably be a mess, or at least much less selective than we want it to be. So even though that's a reasonable answer, it would be much higher yielding and much better synthetically to use the Williamson ether synthesis and rely on that good old SN2 chemistry. Hopping forward to the next one, oof, two more boxes here. This is getting tough. All right, so we got one box and two boxes, and now we have an intermediate, right? So we got to use something to make something in a box that's going to lead to this overall product. All right, and then we have an alkene here. We've got a diol there. Now, some of us might remember that there's a way to do this directly. So we could use OSO4 and do an osmium dihydroxylation in water. And if we want to be better for the environment, we could use a co-oxidant like N-methylmorpholine N oxide and use a very small amount of osmium as the catalyst. So that's the so-called upjohn dihydroxylation, if you prefer to go look that up real quick on Wikipedia. But that won't help us here because even though the upjohn oxidation is a direct reaction in one step to give us the diol, it does use that osmium, and that osmium is toxic and it's a limited resource. And so maybe we'd prefer a two-step method, especially if it helped us avoid the need for that intermediate or the osmium. So looking at this here, two steps. Now there is a functional group we know that looks an awful lot like a diol. And importantly, that functional group happens to be reactive in the presence of acid and water. And what I'm thinking of course, is an epoxide. Because if we had an epoxide here, we know how to make epoxides from double bonds, and that epoxide then can open up at the more or less substituted carbon, depending on if we use strongly basic conditions or strongly acidic conditions. Of course, if it's strongly acidic here, then it would open at the more substituted carbon. And that would be facilitated because it's benzylic, which is even more reactive than a normal carbon would be. All right, and if we think about the epoxide, then we know how to make epoxides, and our favorite reagent for that is MCPBA, metachloroperoxybenzoic acid. And so that ends up being a really great reagent to make that, and then we can just hydrolyze the epoxide open to make the diol, and so that works out quite nicely. Oh, speaking of epoxides, that's exactly what we've got going on here. And now we have sodium cyanide. Now, epoxides opening under strongly nucleophilic conditions. I would, when I think of sodium cyanide, I think about SN2-like reactivity. And so that should occur with inversion of stereochemistry. So you got to go back and recall all of those key SN2 rules. And not only that, it should occur at the less substitute carbon, right? So methyl is better for SN2 than primary, which is better than secondary, which is much, much better than tertiary for SN2 reactions. And so I'm going to open up that epoxide with my strong nucleophile. Now you'll get the intermediate alkoxide, and that, at least preliminarily, is uphill to generate the sodium alkoxide. And let's see here, we need cyanide to go down. And so that, could be an issue. Sometimes you do this with a little bit of water around, and sometimes you also then just work this up in a separatory funnel. And so even though the alkoxide is the initial product of this opening, we hardly ever draw that. What we would draw instead would be the alcohol, where you generate the alcohol from water plus the alkoxide just in an acid-base equilibrium. So that should be good there. All right, last one. Oh, another pesky epoxide. Shown here. Two sides. And let's see here. In this case, now we have HCl. So that's going to protonate the epoxide first. Protonated epoxide. And protonated epoxides tend to react on their more highly substituted positions. And so even though we don't always invoke this carbocation intermediate, in this particular case, we might want to do so because this benzene ring is quite stabilizing to that carbocation, as is the idea that it's already a tertiary carbocation. So this is a tertiary and benzylic carbocation. And so that'll make it one of the most stable that we can form. And because of that, it will likely have some ability to form that carbocationic intermediate. And since we're in the presence of HCl now, we might imagine that Cl would come back and attack. And I'm going to intentionally draw this without stereochemistry now, because even though there's some chance we might be able to get some of that stereochemical retention via an invertive process, because it makes such a stable carbocation, and because chloride isn't a particularly great nucleophile, odds are we'll actually lose most of the stereochemical information that was in the starting material, and we'll have a racemic product. All right, that's it for this video. Hopefully, if you're enjoying these, you can go ahead and subscribe to the YouTube channel, tell a friend about us. And lastly, if you're wondering how all the videos are organized, remember the banner up top tells you what's kind of the key bit, and then the little star on the side tells you what kind of question you'll see in the video. And so hopefully you can use those two pieces of information to make sure you're watching the video that interests you the most. So take care, and thank you for tuning in.